Okay, let's begin. So if there are no questions, let's get started with our discussion on expectation maximization. All right, so that is one algorithm for optimizing a function. Right. So far we have looked at functions and we have optimized them. Right. We have looked at objective functions, losses and likelihoods and everything, and we want to find out what is the parameter that gives you the best value. Right. And we have used methods like gradient descent. We have also seen, actually you have used a method called conjugate gradient descent. We have also seen things like Newton-Raphson method. So there are all of these gradient based methods that can let you optimize, right? However, there's one implicit assumption in all of these methods is that your function is convex, right? By convex we mean that it's sort of smooth and it has one maxima or one minima, right? And if that is true, then your optimization will converge to that value. But if it is not, if it is hard to maximize or minimize, then we need to come up with other methods, right? So EM or expectation maximization is one such method. All right. So let me first give you a general idea of how EM works, and then we will go into how to use EM for estimating parameters for mixture models. All right. So expectation maximization. So the idea is very interesting. All right. So let's say you have some function. Let's call it L of some parameters theta. All right, and theta is here, and let the function look like this. All right, and we want to find the value of theta at which L of theta is maximum. That means that we want this value, right? So how do we get to this value? Of course, one of the things that we have seen is to use gradient descent based methods. But what if the gradient of this is hard to compute, right? In that case, we have this other method called expectation maximization, right? So the way that works is it assumes that, let's say we start at some value of theta. Let's say this is some theta at time t. It's an iterative method, so there is notion of time, right? So at step t, let's say this is our estimate of theta. So we typically start with some initial estimate. So that will be our theta of 0. So let's say we are at time t, right? And this is the value of theta of the function at time t, right? Now what we assume is, let's say we know a function q, okay? Let's say we know a function q at time t, which is like this. Let's say we have the knowledge of a function at time which touches the main objective function at theta t, all right, and it is convex and it is always less than the main function, all right. So let's say this is a function that we know somehow. So right now I'm just saying that, let's say we know this q function. So the property of q is that q of t touches L of theta at theta t, right? Which means that the value of q of t at theta t is equal to, so that is q at time t of theta at time t is equal to L of theta of t, all right? And q of t theta at any theta is always less than L of theta. Well, we can make it L less than equal to at any L of theta, which means that it is sort of bounded by this main function, right? So if we know a function like this, now this, you will have a new function at every theta, okay? So q is not one function. Q is not something like theta cube plus 2 theta square. Not just that, but q will be something like this: theta cube times theta t, which is a constant because we are assuming at time theta t we know what theta t is, plus theta of t log of theta and something like that. So I'm just writing a hypothetical scenario, but the idea is that you have a new function at every time, all right, at every value of theta. So let's say if we know this function, then the way EM works is that at this point it will try to maximize this function, okay. So it will try to find the value of theta at which q at time t is maximized. So that will be this value, and that is easy to get because we are assuming this is convex, right? So that will be that value, and then what we do is we choose that becomes our new theta t plus 1, all right. So now suddenly we are at this point, right, because we found theta t plus 1 by maximizing the q, and then we moved here, all right. And then at this point we again assume another function q, and then we move forward, and at every point what happens is that EM sort of keeps moving towards the optimal by making these short jumps, by assuming that at every point we have knowledge of a function q, and then that gives us the maxima here, then we go here, and then so on. And at one point what will happen is that this will be our function, it touches L at here, and then this will be the maxima, and this will be our maximum value, all right. And then if you theoretically understand this algorithm, you can see that this will converge. Why? Because at every point you're assuming that you have a function q which is bounded by L, right? So it cannot go over L, right? And it is convex. That means that at one point it is guaranteed to give you the right answer, right? So that is sort of a very crude description of expectation maximization, right? But the main question that comes here is how to find q, right? Because so far we have assumed that we have a q, but how do we get this q, right? And that's where the notion of expectation comes, right?
When you say how to find q, you mean how to find the equation?
Yes. Right. So because we know what L of theta is, right? So for example, in our mixture model, we knew what our function is, the log likelihood function that we want to maximize, which looks like this. So for mixture models, L of theta, so we have some parameters all encapsulated in this theta, and L of theta looks like this. Then theta, right? So we assume that we have k mixture components, and each mixture component has some probability of being chosen, that is pi k, right? And then given a mixture component, there is a probability function that we have, a PDF, to give the probability of xi given that parameter, given that mixture component, right? So we know what our L of theta is, but we don't know what q is, right? And if we know the q, then we can do this expectation maximization. Yes?
Does the q change at every point?
Right. The q changes because the q is not only a function of theta, but it's also the function of that starting point, which means that at every point you're assuming you have a q, all right? And that is sort of the beauty of this, is that in the case of latent variable models like mixture models, it is possible to find a q, all right? And then we will talk about how to get that q, right? So the general idea behind the main applicability of expectation maximization approach is to deal with situations where you have latent variables, right? For example, in our mixture model, remember we have this latent variable called zi, right? Where zi is the assignment, right? Zi tells you which mixture component did xi come from, and that is something that we don't know, right? So that is a latent variable, and in these situations you can use expectation maximization. You can also use expectation maximization when you have missing data, right? So for example, you might have lot of what should I say, you might have a training data, right? And in the training data, let's say in one of the x's, some of the attribute values are missing, right? We don't know what they are. So in those cases also, you can use EM to estimate the parameter. So it's a pretty powerful methodology that is applicable in many places, right? But in any situation where you want to use EM, the main thing you want to find out is the Q function. If you can find Q, rest of it sort of falls into place, right? If you have Q, then you can at every step what you do is you figure out what your Q is as a function of your theta and your initial parameter, right? And then you maximize it. So there are two steps that you can see. So in general, EM is an iterative algorithm which goes like this: while not converge, and we can talk about what convergence means, but right now let's assume there's some way to find out the convergence. So while not converge, what you do is you find your Q using current theta, right? And that's, I'll call it QT, and then you find a new theta by maximizing Q of t, right? And then you go back. So that is sort of an algorithmic way of writing what I wrote here, is that you start here every time you find a Q, assuming that Q is a convex function which is bounded by your main function, then you can follow this, right? So the only thing that is missing around here is how do you find this Q, and that is the part that is determined by your problem. So for example, for mixture models there is one way to find Q. For other situations there might be another way to find Q. All right, so today we are going to see, not in too much detail, but just sort of very briefly, how do we get Q for mixture model estimation. All right, any questions so far? All right, so now let us talk more about mixture models, having given you a brief sort of a general overview of what expectation maximization is, right? So just as a reminder, this is what I wrote earlier, right? So you have some theta, right, and you want to figure out the log likelihood of a data set, and that can be written as this, right, where zi's or zk's are the assignments. So it's like a 0 1 number which tells you does it belong to category 1 or 2 or 3 out of these k categories, right? And then this is the conditional probability. One thing that I talked about last time was that, of course, this looks like a nice objective function which is a function of theta. So you can use gradient descent to do this. Of course, when you look at the form of this equation, there is a summation inside a log which makes calculating the derivative very hard. So you can compute the L, you can compute the OBJ val, but you cannot compute the gradient of that very easily. So it's hard to optimize. So that's why we use what we call EM, right? So let me give you a sort of a simpler EM method, and then we'll go into the actual algorithm, right? So one method could be that we start with some guess for theta, all right? So we say, okay, theta is something, and then we compute what is Zi. So let's do it here. Let's say we are trying to estimate the parameters of this problem, actually, here, right? So let's say I'm giving you some training data in one dimension, and the histogram looks like this, but this is just a bunch of points, right? And you want to find out, so theta is this, you want to find out mu1, sigma 1, mu2, sigma 2, and there's also a pi, which is the parameter for z, right? Now how do we do that? So one way to do that could be a simple EM. So let's say this is your training data. You have 0.7, 0.8, 0.3, 0.2, 0.5, 0.6, 0.1, 0.5, 0.2, 0.3. Let's say this is my axis, right? Right. So these are my axes, right? And I want to estimate, so, and I'm assuming that k is 2. That means there are 2 mixture components. So I want to find mu1 and sigma 1, and I'm also assuming each component is a Gaussian, and I want to find mu2 and sigma 2, and I want to find pi. Pi is because we are assuming k is 2, so there will be one value which lets us decide which component to choose, right? So of course we can't, so in the beginning we have to start with some values, right? So let's say we assume at t equal to 0, which is the initialization, mu1 is 1, sigma 1 is 1, mu2 is 0, and sigma 2 is 0, and let's say pi is 0.5, some reasonable assumptions, right? The next thing what we will do is that at time equal to 1, we can first figure out what my zi's are going to be. Find zi's. So these all collectively, let's call this theta 0, right? Parameters at step 0. Find zi given theta 0, right? And we can do that, right? Because what we can do is, for each one of my data point, I can compute the PDF, right? I can compute the PDF. So what I'll do is I'll compute the probability of my data point xi to be generated by the first one, which is mu1 sigma 1, right, times the probability of choosing the first class zi, right? So that will be posted, and there has to be a numerator as well, but to compare it is fine. And the second thing that I will compute is probability of z2 times p of xi given mu2 sigma 2. Apologize for the, well, let's do it a little nicely. So here, so I'm going to compute two values. One is what we call pi 1 or pi times p1 xi, and this will be 1 minus pi times p2 xi, right? So I'm going to write it here, and of course, what is p1 of xi? P1 of xi is just the PDF according to a normal distribution of xi, given mean is mu1 sigma 1, and this would be xi mu2 sigma 2, right? So that is how we'll compute it, right? So what we do now is that since we know what mu1 is, what sigma 1 is, mu2 sigma 2, and pi, we can compute all of these things, right? Because this is nothing but, you know, that standard equation of a Gaussian thing, right? And then so you'll get some values here. You'll get v1, v12, v21, v22. So these are just these values for these different data points, right? And then, so these will all be numbers that you can compare. So then you can choose whichever is the highest, right? And that will give you zi. So zi will be argmax I of these two values. xi, right? So whichever is higher, you will choose that as zi, right? So you can using these values, you can find out what my zi's are, and then so that is part 1, and then part 2 will be to recalculate mu1 sigma 1, mu2 sigma 2, and pi. So we are going to call this theta of 1, so at time 1, right? Because now what will happen is, since now I know what my zi's are, let's say according to these calculations, let's say my zi's are like this. So let's call this zi. So let's say this is 1 1 1 2 2 2 2 1 1 1, which means that according to these parameters, this point should be generated by the first component, these points the second component. So now what you can do is you can recompute your pi, right? So your pi will just be 3 4 5 6 by 10, right? Mu1 will be just the mean of, or the MLE estimate for all the points that are generated by 1, and so on, right? And then you can again go back at time t equal to 2, you again find your zi's and do that again, right? So this has a very strong relation. I mean, it looks very similar to what we saw in k-means, right? We're doing the same thing. You are at every point in k-means, we had some cluster, we had some notion of, instead of these values, we had a cluster centroid, right? At that, and then at every point we were trying to find the best cluster, and then we are recomputing the cluster centroid, right? So similar way here. Yes, go ahead.
So when you recalculate, you're going to recalculate all of the heat?
All you in this step? Right. So in this step, so in the previous step, what you have done is you have computed the zi's, right? Yeah, the index that corresponds to the maximum value, right? Now what you can do is, now you have to recompute all of these things, right? So how will you, so let's go with pi. So pi will just be, because you're assuming that zi, remember zi you assume is a Bernoulli random variable, right? Which means that you have to compute a pi, probability of heads, right? And MLE for Bernoulli random variable is just the number of heads divided by total number of points. So that will be 6 over 10. That's a new pi, right? And then you'll also compute new mu1. So mu1 will be the mean of all the points that have index 1, right? And that will be the sample mean. And then you can also compute sigma 1 same way, and then mu2 and sigma 2, right? And then what you will do is, then you will go to t equal to 2. Then you will do the same thing. You will again recompute zi's and then recompute the thing. So this is sort of a simple EM. Okay, this is not exactly this, which means that this EM algorithm will not guarantee that you will reach here, because it is not explicitly trying to optimize on that, right? It's trying to do a more sort of a simpler approximation, right? But now what we will do is we will look at an actual EM which is guaranteed to do this, guaranteed to reach here by doing this two-step strategy. The reason I showed you this is this gives you a sense of how you would do it in a more crude way, a simpler way, right? Any questions so far? Yes. Well, no, it could be anything. Of course, pi needs to be between 0 and 1, because pi is the parameter for a Bernoulli random variable, right? Which means that it cannot go, it has to be a probability. But the other values are parameters for Gaussian distributions, which could be anything. But in principle, you want to use some reasonable value, right? You can't just use anything, because then you would have hard time converging to the right value, right? Okay. All right, so let's get back here. Right. So I showed you this simple algorithm, right? It's just what I wrote there, but it does not explicitly maximize the log likelihood of the mixture model, right? It's trying to do the same thing, but in a very simple way. But there is a better algorithm. So the better algorithm is that at every point, instead of just finding what is zi, right? Remember here, what we did was, we said that you compute these two values and choose the larger one. Instead of that, what we can do actually is we can use these as the weights. These are kind of the probability that this point will go to mixture 1, and there's a probability it goes to mixture 2. So it is softer in that sense. So instead of making this hard decision, you can use these weights, and then you can compute all of these things in a weighted way. So you choose all of these points to compute the means, but choose them with some weights, right? So that way it will be a little softer, and that kind of becomes more like EM algorithm. So in fact, when you apply the EM expectation maximization algorithm, the answer that you will get looks exactly like doing this weighted approach, right? So that is the idea. All right. So this is the sort of general EM that we have talked about, right? So every time you start with some value of theta, and every iteration you update theta such that you're going towards the right answer, and then keep doing that, right? So the main thing is, of course, that you want this q. Remember that, right? So we want this function q, which is sort of this function that is bounded by the actual function, right? So in the case of latent variables, it's actually easy to compute this q. It is nothing but the expected value of this function, right, at that, given this as my current estimate, right? So the idea is this, that we don't know what our zi's are, right? If we knew our zi's, then this whole process would have been very easy, right? But we don't know what our zi's are. Zi's are our random variable. So what we do is that we compute the expectation of this function over all values of zi, right? So what is expectation? Expectation is if I give you a function, the expectation of that function is the value of that function at all possible values of the argument times the probability of that argument, and you sum it over all possibilities, right? So if you compute the expectation, then the function that you get, new function that you get, will be your Q. And the reason that is true is because of something called Jensens inequality, that I'm not going to talk much about. But in general, it's actually a very interesting concept. So if you are interested in latent variable models and expectation maximization, I would strongly suggest that you sort of read up a little more on, or try to understand Jensens inequality a little more. But in the case of probabilistic models, Jensens inequality says that the right nomenclature. Is that if you have a convex function, right? So if you have a convex function, then the expectation of a function of x, right, will always be greater than or equal to the function of the expected value of x, right? Where expected value of x, if x is a random variable, is given by summation x p of x, right, for all values of x. Or if x is a continuous random variable, then it becomes an integral, right? And the same way, expected value of a function of x, any function of x, is given by f of x times p of x over all possible values of x, if x is a discrete random variable. And if x is a continuous random variable, then it becomes a function. All right, so this is sort of the general idea behind Jensens inequality. The reason that is useful is that what happens now is that, let's say we have some L of theta, right? Now L of theta is some function of your, I mean, I'm talking about mixture models, right? So remember that L of theta is also what we call if we knew, let's say if we try to write it as the zi's in terms of zi, right? So if we knew this zi, but zi is unknown, right? So you can think of L of theta as a function of zi, and then what you do is, instead of computing L of theta, which we cannot because we don't know what zi is, we try to compute the L of theta for all values of zi. So it's like an expectation over all values of zi, right? And then what we do is, but that is sort of harder. So instead of doing that, we use the Jensens inequality and compute the expectations of L of theta. Okay, so we compute E of L of theta, and that becomes our Q. And because of Jensens inequality, it means that it will satisfy this behavior. All right. So I'm not going to. So I realize I'm going a little fast because it's sort of not core part of our course. So don't worry about it if you're not following it much. So if you do want to follow it more, come back and talk to me in my office hours, or we can talk about it in some other place as well, or you can read up on your own and everything. But the general idea is this, that we use Jensens inequality to compute Q as an expectation. So for this case, Q is just the expected value of your L of theta for all hidden variables that you have, and then you use that in your EM. So you compute Q, and then you maximize it in M step, and you keep doing that. All right, so this is what it looks like. Right, so Q of, so we compute this Q at any time step t minus 1. It's expected value of L of theta given D and a previous estimate of your thetas, and then we maximize it. At every step, we compute E. So there are two steps. There's E step in which we compute Q, and then M step in which we maximize this to get a new value of theta, and we keep doing that. We keep doing that until we reach the top here. All right, so this is just what I drew earlier. So this is the EM operation. Any questions so far? There will be one question. Oh, in the gradients for this week is more about clustering, because somehow my schedule got a little changed. But so both problems this time are about clustering, and then next gradients I will have problem about EM. So wait till then to get a better sense of this, right? So now let's look at how to do this for mixture models, right? So in mixture models, we know what our this is, L of theta. So what we do is we compute the expectation of that, all right? And this expected, so I've skipped a lot of steps because I don't want to go into the math, but the idea is you can easily compute it because you can compute the expectation. Now, expectation of a function is easy to compute because as long as you know what is it a function of, so it is a function of zi's, and what are the probabilities of zi, so then you can do f of zi times p of zi d, all possibilities of zi, right? So you can do that, and this is what you will get. So you will get q, and then you can maximize that, and then you get new value of theta, all right? So in general, this is what you get. You in each step you compute these values. We call these responsibilities. So if you look at it, this is nothing but the posterior probability of, it's basically this, right? And this looks very much like what I was talking about in the weighted version, right? So you compute this, which is the probability of the point I to be generated by mixture component K, right? So you can compute it by using all of these. These are all the thetas that you have. You have the pi, and you have this will be all the means and variances, right? So you can compute this, and then you of course compute Q, and in the M step you maximize it. So if you do the maximization, the math becomes actually pretty straightforward, and it looks like that. So in the M step, the new pi will look like this. The new means for each mixture component will look like this. The new sigma will look like this. So in the case of mixture models, in the case of actually Gaussian mixture models, the math is very simple. So you don't actually have to every time maximize and compute Q. By doing the math, it essentially boils down to this. In each step, you compute these Ri's, Riks, and in M step, you compute this, and you keep doing that until you converge. All right, any questions so far? All right, I want to give you a quick demo before we end this discussion. All right, so we were looking at this earlier, right? So, so if you look at this this notebook, you will see that I have written for a one-dimensional data set in which D is 1. And for two mixture components, I have written like a EM algorithm, right? So what we do is we start with some initial estimate of your parameters. So we have mu1, sigma1, mu2, sigma2, and pi. Okay, so I start with some estimates, all right? And then what I do is in each step, I compute those Ri's. So we call those responsibilities. Actually, here I treat them as gamma. So at every step, I compute gamma, and then I compute. So this is what we call the E step. And this is the M step. And then at every time you get a new value of your thetas, and then you keep going up, and you also check for convergence. So convergence here, actually I'm cheating. I'm not truly checking for convergence. I'm just saying if I've run it for so many iterations, you can stop. But in general, what you can do is you can check if your thetas are not changing too much, then you mean that means you have converged. So if you run this algorithm on the data set that I had shown earlier, which looked like this, right? So if this is the data set, I mean, I'm showing you the histogram, but this is the data. Then if you run EM, this is what you get. This actually is, it matches exactly the parameters that I used to generate the data. So this shows that EM does converge to the right answer, all right? I want to give you one more example. So now you can actually use that new model, right? So this is my mixture model. I can use it to generate new data. So this will be the histogram of the new data, and you can see that it matches very much the training data, right? That makes sense, right? So I wanted to give you one more demo for two-dimensional case. So let's say you have 2D data. So I have this data set that's pretty popular. It's called Old Faithful. So if you've been to Yellowstone, there's a geyser or a fountain, a hot water fountain, which is called the Old Faithful. The reason it is Old Faithful is that it erupts every so many minutes, I think, right? So there's a data set where somebody went there and it measured the height of the fountain, the eruption, and the duration between two successive eruptions, right? So they wanted to see. So that data looks pretty interesting. So if you look at the data, it looks like this. So these blue points are, so each blue point here is one of the eruptions, right? So, and this is normalized height and this is normalized duration. So you see there are two clusters, right? So now what the problem for us is, can we learn a mixture model? All right, so in this mixture model we are assuming that there are two components, because visually we can see there are two components. So what I've done here is, in this cell, is that I've implemented basically our mixture model. All right, so at every time I start with some initial estimate of my mu's. So there are two mu's, two sigmas, and a pi. And then what I do is I run my EM. So in each step I compute the gammas or those RVs, RIKs, right? And then in the M step I recompute my mu's and pi's and sigmas, all right, and I get this. And then what we see here is that now in these sets of graphs you will see how the model works, right? So in the beginning this is my data, and these circles kind of denote the Gaussian that you are fitting. So in the beginning I started with one mean centered at 1, -1, one mean centered at -1, 1. So these are the two means. These ellipses just show the first variance circle or contour, right? In the second step, what happens is that it starts sort of moving these things, right, towards the right answer, and then it keeps doing so, E and M, E and M, E and M. So what you'll see that slowly it starts sort of converging towards the right answer, and in the end this is what you get, right? So the colors indicate the which mixture component each point belongs to. So in the beginning, of course, since we started with a random guess, these red points belonged to one mixture component, these points belong to another one, but as the EM algorithm works, it starts assigning them in the right way, and at the end this is what you get. All right, so now this is something that you could have done with k-means as well, right? Because in k-means also, if you remember the demo, the same thing happens. You start with some estimates for your centroids, right, and then you keep updating them until you converge, right? But in k-means what would have happened was that all of these points would have gotten the red color, and all of these points would have gotten the white color, right? But here, because this is EM, that's an example of soft clustering, you will see that some of these points, the color kind of indicates the belonging, okay? So the reason these points are slightly darker in shade is because they belong to both clusters with some probability, right? Or to the both components. So that is why this is different from k-means. K-means would give you what is called a hard clustering, but this one will give you the probability. So it's a soft cluster. All right. So that's it. Yeah. Any questions about it? All right. So okay. So this is sort of the general idea behind mixture models. And so as I said in the beginning, right? So we started with this discussion of latent variable models. We said there's this notion of latent variable models in which you have some observation x, and these x's depend on some hidden random variable or latent variable z, and then we want to figure out what is p of z, p of x of z, and everything, right? So one of the example, of course, is what we've seen, mixture model. Now we will look at this another example of a latent variable model, which we call factor analysis. Okay, so of course we are kind of towards the end, so I'll quickly introduce it and then we'll talk about it later. Just give me a second. I don't think I compiled it well. All right. All right. So we're going to talk about latent linear models. So as I said, right, so in the case of mixture model, we said that we have one latent variable, zi, right, which takes values, which is a discrete random variable. It takes k, one out of k values, and then we have these two probabilities that we want, right? But what if zi is not a discrete random variable, but it actually is a vector by itself, right? So what if the latent variable is a vector in L dimensional space? So we are assuming that our x is in some d dimensional space, and what if there is a zi which is in L dimensional space, right? So in that case, of course, we can't use this, right, because our random variable is no longer a discrete random variable, so we cannot model it as a multinuclear or a Bernoulli distribution anymore. We will have to model it as a continuous distribution. So one example, of course, is as a Gaussian random variable, right? So if we have this kind of setting, so now some things change, right? So now we cannot compute the probability of zi to be something because zi is a continuous variable. So now we will have a PDF for zi. So one possibility is we can model zi as a Gaussian random variable with some mean and some variance, covariance, right? And now the xi, right? Xi, what we observe will be a function of zi like this. So earlier it was like this, right? Because zi only took 1 out of k values, but now our zi will be in this L dimensional infinite space. So you will have to do an integral over all possibilities of zi, and this becomes the expression, right? So this kind of model is known as a factor analysis model. When we assume that our zi's are a vector, okay, when we assume, so if we assume that my zi is a discrete variable which takes values from 1 through k, then it is a mixture model because zi tells you kind of which mixture it belongs to. But when we assume that zi is actually a vector itself of continuous values, then we call it as a factor analysis model. All right. So now we are going to look at it a little more later. So then the question becomes, okay, how do we use it, right? What is the use of it, right? We can see we saw a clear use of mixture models to do clustering, to do soft clustering, and also to do like a conditional probability distribution. But now how do we use zi? How do we use this kind of model, this model where you get a dependence between xi and zi? So think of it like this, right? So the way to interpret a factor model, actually we call it factor analysis model, is that we observe some x, right? We observe xi, okay, and let us assume that all xi's belong to R2. That means that they are in a two-dimensional space, right? So what we assume is that we observe some xi, let's call it x1, right? And we assume that zi, which is the hidden random variable, belongs to R, so just one-dimensional space, which means that on this number line you have some z1. Okay, so what happens is that in mixture model, remember, we were tossing a coin to choose our z. Here, instead of tossing a coin, we are drawing from a random distribution, and then once we get z1, then we choose that to compute what my x1 is, right? So we are trying to, in some sense, you can see that there is some relationship between your data in two-dimensional space and this hidden data in one-dimensional space. So in some sense, the direction that I'm trying to go here is that this gives you some sense of a dimensionality reduction, right? Because what you're saying is that you observe some data in 2D space, but in reality, there is some hidden variable which was in one-dimensional space which actually generated this 2D data, right? So our task is to learn this inverse mapping, right? Now we don't know how this mapping went in this direction, right? So somehow there was a z1 that we sampled from a normal distribution, and then we used that to get this x1, which is in 2D space, right? So maybe we did some mathematical computation like x1 is nothing but z1 times sine of z1 comma z1 square cosine of z1 or something, right? But we don't know this mapping, right? So in factor analysis models, our task is that we are given bunch of x's, right, xi's, these are all x1, x2, x3, x4, and we assume that they are all being generated by this two-step process where a z2 would have been sampled and that would have been then used to do this and so on. Now we want to, and we are somehow in our mind assuming that it's all sort of some kind of a functional transformation, but we don't know this functional transformation, right? So now what we want to do in factor analysis model is, given these xi's, we want to infer what these zi's would be, right? So in some sense we are converting our two-dimensional data into a one-dimensional data, right? So you can think of it as a kind of a dimensionality reduction, and in factor analysis we will see that these will have some relevance, some semantic notion to it, which means that this z would be capturing some inherent latent property that gives you these x's. So this will become more clear next time when we look at an example. So today I just want you to go back with this sort of a notion that factor analysis is an extension of mixture models, in which instead of assuming that zi's or your latent variables is discrete, you assume that they are continuous, right? And geometrically what I've shown you is that it gives you some notion of a dimensionality reduction, and we will talk about it more on Friday.